I am Gabrielle, and I'm doing homework. I'm Gabrielle, and I'm going to be doing homework for part A. So the question says that we need to derive some differential equations for 3 tanks. So we have 3 tanks in our flow system. Each tank is draining into the other. And we're starting off with a draining in. So this is going to be Qn, and this is starting off at 0.1 meters cubed, and it progressively is going to get to 0.15. So it's going to be increased by 50%. So the next thing is we know that our cross-sectional area of each tank is going to be 0.1. Well, this is going to be actually 1. It's going to be 1. It's going to be 0.5, and then 2. Okay. So we also know that our area of our drainage hole of 1, 2, and 3. So our cross-sectional area of the draining is going to be equal to 0.01 meters cubed. Okay. So nextly, we are trying to figure out our heights. We want to know what our heights are changing in our tank as the system continues. So when we're at 1.1, we're at a steady state. And then as it increases, we want to know how the heights are increasing through this in change of time. So we're having a differential change in height due to time. So the first thing that we want to do is to find out what our height is going to be. So what our liquid in our tank is going to be. For the first, it's going to be our differential change in our cross-sectional area of 1 times our differential change of height due to time. Okay, and so this is going to be based off of our flows in and our flows out. So our flow in is going to be Qn for the first. So Qn, and then we have to know what we're subtracting by. So what is our Q out going to be? We know our differential. We know our cross-sectional area of the flow out, which is going to be AD1. So now we need to know what our flow out is going to be. What is our velocity? How fast is this leaving? So we know that our Bernoulli's equation can tell us this. So we have P1 minus P2, well, P2 minus P1 over our density plus our V2 minus our V1 over 2 is going to equal, well, plus our G, so our gravity times our Z2 minus our Z1 is going to equal 0. So the first thing that we know about this equation is that there is no pressure change, so this is going to be equal to 0. And then this could be just as height, so it's going to be GH, that's going to change too. And then the velocity inside our tank is not going to be changing, so we know this is just going to be V2 over 2 plus GH. So if we move everything over and we solve for V, we know that V2 is going to equal the square root of 2GH. Okay, so now this is the velocity that's leaving the tank. So if we multiply this by our cross-sectional area of what's leaving our tank of our flow, this will tell us. Okay, so the next thing that we know is as this is draining, it's going into the other tank. So to find out our second and our third, we have our cross-sectional area of the second due to height and time. And this is going to be A D1 square root of GH minus our cross-sectional area. So this is what's flowing out is going into the tank. So this is what is being added, the liquid that's being added to the tank. And then we're subtracting it by what's leaving the tank. So it's going to be the same thing, but it's our cross-sectional area, our second, which is 2GH. And then we just have our last one, which is 2 to the third DH dt equals our cross-sectional area, the second, square root of 2gh squared minus r h3 square root 2gh squared. Okay, so we know this. So also, we know that this is a steady state to begin with. If it's a steady state, that means our height is not going to change. And if our height is not going to change, that our dHdt can be added to 0. So we need to find the initial heights. And this is how we're going to find the initial heights. So this is going to change when it changes by 50%. But to begin with, when we're at a steady state, we can find the initial heights of both things. So if we move, so to find the initial heights of our tanks, we're going to be using the differential flow out. So it's going to be, well, we're going to be making this a 0. So 0 equals Qn minus HDI square root 2GH. And this is going to be pretty much for everything, and we're just going to change our cross-sectional area of the inside because everything is going to be at a steady state of 0.1. So if we move this over and we solve for it and solve for our H, we're going to have Qn at the top, height 1, so Qn, and then we're going to be divided by our cross-sectional area of our drainage times 2GH. And then since that is squared, we have to just square this square rooted, so we have to square these, cancel it out. So now that we have height 2, and then we just have to change this to 2GH, and our height 3, which is going to be Q squared of D3GH. Okay, so now we're going to use this equation. We're going to use this to just solve for our differential equation to find the height of changes. These are going to help for our initials of our height. And then that's pretty much it. So let's get to our coding. Okay, so I'm doing part A, part 2. So what we just derived for our 3-system tank, I'm going to do was solve IDP for it, solve the IBP for it. So the first thing that we want to import is, let's import numpy as MP, and then from scipy dot integrate, because we're going to be integrating our differential equations. We're going to import solve IBP. Okay, so the next after we solve for our differential change in heights of our 3 tanks, we're going to want to graph them. So from plot ly, we're going to make subplots. We're going to import make underscore subplots. Okay, so the next thing that we want to do is we're going to initialize our values. So we have gravity, that's 9.81, and then it says that our inflow system, so our Qn initially at a steady state is going to be 0.1, and then our Qn is going to change, and this is going to change by 50%. So it's going to be 0.5 times our Qn initially. Okay, so the next thing that we know is that our cross-sectional area of 1, our cross-sectional area of 2, let's do capital Q1, cross-sectional area of 2, and our cross-sectional area of 3 are going to equal 1.5.2. Okay, so the next thing that we know is we know that our drainage hole of every single tank is going to be 0.01. So we're going to do our cross-sectional area of our drainage hole is going to equal numpy dot array, and it's going to be 0.01, 0.01, 0.01. Okay. And then lastly, we need to know that our time, because it's going to be based off of time. So the time that we're going to end at is going to be 1,000. Okay. So the next thing that we want to do is we need to initialize our height. So our initialize our height is when we derived our equation. So it's going to be Qn initially squared divided by our cross-sectional area. Our cross-sectional area of our drainage hole squared times our 2 times our gravity. Okay, so after we know that, let's define our function. So it's going to be define of the HDT. So what is the height changing in all 3 tanks? And so this is going to be T times H. So the next thing that we want to do is, after we know that, we can do is we can solve for our Q out. Our Q out, we know, is going to be our cross-sectional drainage hole times our, well, Q1, Q2, Q3. Well, we have our leaving flows from both systems is going to equal our cross-sectional area of the drainage hole times, and we're going to times this by 2 times G times H, and this is going to be squared. Okay, so now we know what's going out, so we just have to subtract pretty much what's coming in, what's coming out, and then we divide it by our cross-sectional area. So this is what we want to return. So we want to return, we're going to return our, so we have Qn to be the first tank, it's going to be Qn, then we're going to have our Q1, and then divided by our cross-sectional area of 1, and then we're going to have Q out, well, we're going to have Q1 minus our Q2 divided by our cross-sectional area of 2. And then we have Q2 minus our cross-sectional area of 3 divided by 3. Okay. So the next thing that we want to do is, so after we found our cross-sectional area of our heights and our differential time, after we found that, we can use our solve IDP function. So our solve, we can use solve IVP. So in this function, we just need to know what our function that we're trying to solve. So it's going to be DHDT. Then it's going to be from 0 for our time, 0 to the time ended that we specified. And then we need our initial height, so H0. And then we just need to have our dense output. So our dense output has to be true because we want this to be specified at different times, or the times that we specified. So we need this. So let's see what it says. Okay, so it says specify SciPy integrate. So this means that we can change the times that we want. So this, let's put resolution here. Okay, so the next thing that we want to do is we need our x-axis. Our x-axis is going to be our time. So t-plot, the time that we're going to plot, is going to be an NP linspace. And this is going to be from 0 to Tn, and so it's going to be 500 points. Okay. So after this, after we have our t-plot, now we can use our resolution solver and just do this based off of the times that we specified. So then this is going to give us our heights. Our heights have 1, 2, and 3. So height 1, height 2, and height 3. So the next thing that we want to do is we're going to make we're gonna do fig, make subplots. So we're gonna make our subplots, and then the next thing that we want to do is fig dot add underscore scatter. So this is going to be a scatter plot, so our x-axis is going to be t, and then our y is going to be our h1, so our height at 1, and then we're going to have our name just be height 1. It's going to be at height 1, and then we just want to have a mode equal our lines. Okay, so I'm just going to copy and paste this and do this 3 times. So, well, 2 times. So this is going to be changed at height 2, height 2, height 2, height 3, and height 3. So shift and we're going to do our layout. So our fig dot update our layout. So we want this to be a height of 600, and we want our width to be 800. Let's just see what we get. Okay, so this is good. So this is pretty much just saying our height 1 is going to level out at 11, like I think 11.5, and our height 2 is going to be a little slower, but it's also going to level out at a height of 11.5, and then our height 3 at 10,000 at 1,000 is going to be at 11, but it's still reaching up a little bit. So that is our answer.